And we are live. Hi, everyone. Very nice to see you today. This is our guest speaker program, regular monthly talk that SJAA does every month. Um, we have we, we have planned it on a different Saturday than typically we do it. Typically, it's a full moon weekend. We try to do it on, so it could have been the last weekend actually. But I was out of town, so it's a big deal at this time. So some of us, I'm aware that SJ also has an event going on at the moment, which is a Star Party. So that might explain why we have less number of people here today. But nonetheless, we have another very interesting topic that Curtis has brought us. And before I let him start on it, I just want to quickly introduce him. He's a physicist who has spent 40 years working on development and commercialization of new technology in defense, telecom, and data storage industries. He has recently retired after 17 years at Western Digital and now enjoys more time to view the night sky. What I found very impressive in his bio is that he purchased his first telescope, a Unitron 60 mm refractor, with the money saved from his paper route. So I for one, definitely want to hear that story. And without further ado, I will have Curtis start his talk now. Thank you, Curtis.
All right. Can you just want to confirm you can hear me?
Yes.
Okay. Yeah, I was always interested in astronomy as a kid, read a bunch of books on astronomy. And eventually I saved up enough money and convinced my parents to let me spend that sum of money, which would have been a lot of money in those days, for a 60 mm. It actually was called 2.4 inch refractor from Unitron. And I still have that telescope. So it's an F-15 telescope, as you might imagine. Back in those days, the optics capability were not what they are today. So anyway, it was a good telescope for looking at the moon, the planets, the sun, stuff like that. All right, so a little bit more about me. I got back into astronomy in about 2008, and I have spent a majority of that time doing electronically assisted astronomy. When I look through an eyepiece, even at a dark site, it wasn't what I wanted to see. So I got involved very early on with using cameras to view deep sky objects in real time. I've done that for the better part of 12 years. And then more recently, I've begun doing some astrophotography. But 2 years ago, not 2 years ago, okay, we're frozen up here. Let's see. There we go. So like many people, I used these big, heavy lead acid batteries that you take into the field. In fact, sometimes I would carry 3 of these 100 amp hour batteries with me because I had my son some of the time with me. And at some star parties, you can use a generator if you're on the periphery, and then you put the generator far away. And I used that for a while. And I began to notice one of my astronomy buddies who used to set up right next to me at Golden State Star Party every year was setting up further and further and further away. And that's because even though the generator was way 100 feet away and I had a baffle around it, you could still hear it. And he was polite. He didn't complain. So I said to Chris, hey, Chris, this was back in 2019. I said, next year, I'm going to be solar. Well, next year was 2020 and Golden State didn't happen. But I spent much of the time, the last 2.5 years, investigating lithium technology to replace lead acid technology. And I did that by doing a general review of lithium battery technology. And I find a lot of people only know this sort of skin depth. They know the kind of lithium that explodes and burns and stuff like that. And they have a misconception that all lithium is unsafe and so on and so forth. And also that all lithium is very expensive compared to lead acid. And I think I'll show you tonight that's no longer the case. I talked with multiple vendors and manufacturers. I looked at reviews, ratings, specs. I even toured one of the factories up in Reno, Nevada, which is a Battleborn factory. Battleborn, you see a picture of their lead acid battery there. And they were kind enough to talk to me technically and take me on the floor, and I could see exactly how they build, test, assemble their lithium iron phosphate batteries. And also Jackery has an office down the street from one of WD's facilities in Fremont, and I contacted them. So I did a lot of homework. And then I was able to get some of these companies to send me their equipment. And as you'll see, I've tested a lot of different solar generators and batteries, and I couldn't afford to buy all of those just to test them and report on it. So these companies are kind enough to send those to me. They don't pay me, and they don't have anything to say about my review. My review is strictly my review. So you see down at the bottom left, the Jackery, their 1,002 watt-hour model. Solar generator with their solar panels, and my telescope, which is a C11 on a software BISC Mighty mount. And on the right, you see a Battleborn battery powering the same setup in a different trip. So I'm not the world's expert on lithium power supplies, but I have gathered enough information that I think I'm qualified to help those of you who are curious about this technology. And let me go through some of that with you here tonight. And if you have questions, go ahead and ask. So the first question might be, well, why lithium? So I put together this chart of different features. So let's look at a lithium 100 amp hour battery compared to an AGM, which is a lead acid battery, absorbing class matte, which is where the typical lead acid battery technology is today, right? It doesn't spill. One of the safer, easier to maintain, not much to do. So you look at the lifetime, lithium is twice the lifetime. You look at the discharge cycles, it's almost 10 times the number of discharge cycles with a lithium battery as with an AGM battery. And the other thing that is significantly different is you can fully discharge a lithium battery without damaging the cells inside. And this is one of the most misunderstood aspects of lithium batteries. People will tell you can only discharge it by 90%, by 95%, 80%. That's not true. You can discharge it 100% till the battery shuts itself off. And we'll talk about why that is. And you will not damage the battery. You will still get the manufacturer's spec, which in most cases is at least 3,000 full discharge cycles. Now, an AGM battery, you really cannot discharge it more than 50 to 60%. So 12.06 volts. And if you go lower than that, you're going to damage the cells inside, and you will find you don't get the 450 to 550 discharge cycles. The weight difference is pretty obvious. The other thing that is pretty clear on lithium batteries is it has a very flat voltage profile. So it makes it hard to tell where you are in terms of capacity by measuring the voltage, whereas AGM lead acid is pretty steep. The most significant difference between the two is something called a battery management system, which all lithium batteries have. If it doesn't, do not buy it, whereas AGMs don't have that. We'll dig into that later. You can charge lithium much faster at a higher current than you can lead acid, has no memory effect. It's self-discharge, which means if you sit it on a shelf somewhere, it will discharge at about half the rate as an AGM, which means you really don't have to do much maintenance on it, once every 6 months. Now, cost of a lithium iron phosphate battery will run anywhere from $400 to $800. I'll show you some examples of that. You can find some outside of that range. Obviously, there's a million out there on the market, but typically $400 to $800. AGM is $180 to $290. Well, why wouldn't I buy an AGM? Well, look at the upfront costs per watt hour. If you divide the capacity, remember, lead acid battery, you can only discharge by about 50 to 60%, whereas a lithium battery, you can fully discharge. So you get all of the energy in there that they say is in there. And you look at the cost difference is now minimal. And if you look at the lifetime cost, because you can run this thing for more than 3,000 cycles, lead acid is far inferior in terms of lifetime cost. So the idea that lead acid is cheaper is no longer true. You may go in the store and pay $180 versus $400, but then in the field, you're going to need 2 of those batteries compared to 1 lithium iron phosphate battery. So that's why I think you should think about lithium if you're planning to improve your power in the field setup. Now, there are many different lithium chemistries that are used. I've listed some of them here. The 2 that are the most common and that we'll be interested in are lithium iron phosphate, which is in most standalone batteries like this battle-born battery. This just looks like a standard battery. It's got a positive and a negative terminal. The package is very similar in size, identical to AGM batteries. So that's one chemistry to pay attention to. And the other is lithium nickel manganese cobalt oxide. So that is commonly referred to as NMC for simplicity. And you'll find that in most solar generators. Now, why are these 2 important? Lithium iron phosphate has a very high number of life cycles. At least 3,000 is the typical spec. Some say 4, some say 5,000 full discharge cycles. It also has a very high thermal runaway temperature, and the nominal cell voltage is about 3.2 to 3.3 volts. So you'll find 4 gangs of cells, either a single cell or a gang of cells in series. 4 times 3.2 gives you the 12.8 volts, which is typical of a lithium iron phosphate battery. Now, it has a low specific energy.
That's what I have.
Go ahead. Question? No? Okay. So one of the things that isn't great about it is it has a low specific energy density. So it tends to be a little bit heavy given the amount of energy in it. That's why it's primarily used in RVs and boats. Now, lithium nickel manganese cobalt oxide, or NMC, has a very high specific energy density, like almost twice that of lithium iron phosphate. And it also has a pretty decent thermal runaway temperature, but the number of cycles is on the order of 500 full discharge cycles or more. Now, think about 500 discharge cycles. If you went out in the field 5 nights a month, every month for a year, that's 60 full discharge cycles. That's almost 10 years it would take you to use 500 cycles. So even though 500 cycles is a lot less than 3,000, don't be shy about NMC because that's probably more cycles than you're going to be able to use. Now, its nominal voltage, cell voltage, is much higher than lithium iron phosphate. That's 3.6 to 3.7. So when you put 4 of these in series, you get 14.4 volts. And that's not where we want to operate, but that's why you'll see that these solar generators have an internal voltage regulator. So you'll find NMC in things like power tools, electric bikes, electric cars, and solar generators because of the high specific energy density. So let's take a look at a typical lithium iron phosphate battery. What's inside? So on the top right, you see a battle-born 100 amp hour battery. On the bottom right, you see an ampere time 100 amp hour battery. Boy, they look very different. And they are, because battle-born uses these cylindrical cells. You see the little round cells there. And ampere time uses prismatic cells, which are basically little rectangular boxes. So with the cylindrical cells, they only have about 3.4 amp hours of capacity per cell. So you need a lot of them. So you put 30 of them together and you end up with 102 amp hours of capacity. And then you have to put 4 groups of those together to get 12.8 volts. So they have a lot more cells in there, a lot more connections, and they're cylindrical cells. Now, ampere time, which is a much cheaper battery, uses only 4 cells, 4 prismatic cells. But these cells are, each one is 100 amp hours of capacity. Put together in series, you now have a 12.8 volt at 100 amp hour battery. So a lot less connections in there, a lot simpler to build and put together, which is why it sells more cheaply. But if you lose one cell in a prismatic cell, the voltage will drop down by 3.2 volts. So you end up with 9.6 volts, and the battery is effectively useless to you. On the other hand, you can lose several cells in the battery above, and you probably wouldn't even notice. You won't notice the voltage drop, and you probably won't notice the capacity by much. So they each have their pros and cons, and that's why you'll see these wild price differences from $400 for ampere time and $800, $850 for Battleborn. Now, I said before, there's a key difference between lead acid batteries and lithium batteries, and that is the battery management system, also called a BMS. Here are pictures of two BMSs. So the function of the BMS is an electronic brain inside the battery. A lead acid battery just has cells in there, and it doesn't have any electronics in there. So when you start drawing current from it, there's nothing to stop you from drawing the current below the minimum cell voltage of a lead acid cell that will prevent damage to the cell. You can just drain it down to the point where the cell is now damaged and won't have the capacity it's supposed to have, even when you recharge it. But in a lithium battery, whether it's a solar generator or a standalone lithium iron phosphate battery, they have this BMS, and it has the following functions. It's there for short circuit protection. It prevents you from overcharging, it prevents you from over discharging, and it also balances the cells inside the battery. So make sure no cell gets overcharged compared to its partners, and no cell gets more discharged than its partners. And it will have a low voltage disconnect. So once the voltage goes to a certain level, which is the minimum safe voltage to not damage the lithium cell, the battery management system will cut off the output abruptly. And that's the key to allowing 100% depth of discharge without damaging the internal cells. Now, once you finish your 500 full discharge cycles on an NMC solar generator, or your 3,000 full discharge cycles on a lithium iron phosphate battery, the battery is not going to be dead. It will still have somewhere between 75% and 80% of its original capacity. So it'll just be degraded from a 100 amp hour battery to maybe a 75 or 80 amp hour battery. The battery management system is also there to protect against charging at too low of a temperature, which is definitely something you should not do with lithium batteries. The spec on these ranges from 32 degrees Fahrenheit or freezing. Some go down to 25 degrees. And then there's a high temperature spec of 135 degrees. Hopefully we're not in those environments of 135 degrees and worrying about charging or discharging in those temperatures. So not all BMSs are created equal. I put a link here to the Battleborn BMS. You can see what it looks like. That's the one on the upper left. And one from a battery on AliExpress. Oh, that's a really great cheap battery. Well, take a look at the BMS in there. If it doesn't have the size of wires and the soldering that you should have, you kind of wonder how long it's going to last. So there are many, many lithium iron phosphate batteries on the market. There's dozens and dozens that you'll find on Amazon. I've listed a table with quite a few different ones that are pretty common. Many of you may have used Talent Cell batteries. I own this particular one here, which is the 83 watt hours. This is a pretty good one. I think the watt hours to cost is very reasonable. And I use this with a 6-inch SE, Celestron 6-inch SE, and when I'm doing some electronically assisted astronomy as outreach. So it's a very small battery, doesn't have a lot of capacity, but it'll work fine for something like that. Then there's the Celestron power tank. And if you look at that one, you're paying quite a bit per watt hour for that. just because it has Celestron name on it and has some convenient ports on it. And the last four down below are typical lithium iron phosphate standalone batteries, and you can see the prices vary considerably. Like I said, Battleborn tends to be on the expensive side. Ampertime tends to be on the least expensive side among these batteries. So just be careful. Lowest cost is not always the best choice. I've tested Ampertime. I'm pretty happy with it. I only tested it because I saw a teardown video. I saw what's inside, and I was impressed with the quality of the components inside. So I don't have a problem with their build and materials. I think it's pretty good. Battleborn, of course, is an excellent battery. It's built here in the US, up in Reno, Nevada. You can pick up the phone and give them a call if you have technical questions, if you have service requirements. You can even stop by, call ahead. They'll give you a tour of their factory. And Bioenno Power is a distributor in Southern California. They're very common in the ham radio business and radio controlled hobby as well. And he has a pretty big following. But I'm sure he uses a contract manufacturer in China to build his batteries, whereas Battleborn batteries are actually made in the US. And Ampertime is also a Chinese company. If you need service from them, you send them an email. But I did send them an email just as a test and pretended I had a technical issue. I sent it in the afternoon, and late that evening, I got a reply back, and the guy gave very good, clear explanation of what the solution to the supposed problem. I didn't actually have a problem, but I pretended I did. So I was pretty happy with their customer support. Now, let's talk about solar generators. These are completely different devices. Solar generators have a bunch of features built in them in one standalone package, which is not what you get with a lithium iron phosphate standalone battery. So you see two different ones here. This is a Jackery 518 watt hour one on the left, and a Max Oaks Blue Eddy 500 watt hour on the right. Typically, they'll have DC power ports. They will all generally have the old cigarette lighter port, which is voltage regulated, as I mentioned before. So the voltage coming out of that won't be the 14.6 volts I mentioned before. It'll be regulated around 13, 12.8 or 12.75 volts. They may also have additional ports on them. And so the Jackery on the left has two ports there with proprietary outlets, and you have to get an adapter to that. The Max Oak has two, which use our typical 5.5 by 2.1 millimeter sockets. Those are 3 amps maximum each port, and the Jackery are 7 amps maximum each port. And I tested those, and they can actually go a little higher, but I wouldn't exceed the manufacturer's spec. In addition to DC power, though, a solar generator has a pure sine wave inverter. So you see the Jackery, this model of Jackery has a single AC outlet. The Max Oak has 2, and the Jackery 1000 has 3 AC outlets. So if you want to run your laptop, something like that, and you don't have a DC adapter, you can run it directly off of one of these solar generators. They also have multiple USB charging ports to charge your laptop, your cell phone, whatever. The other nice feature, when you go to recharge this with a solar panel, you don't need a solar charge controller because it's already built in. So they have a port. You just plug in the cable from the solar panel, and this thing regulates and charges. Very simple. They have displays, they have a power meter. They'll show you the state of charge. Of course, they have the built-in battery management system, and they also have an AC wall charger that's included with these. So you can charge these with AC. You can also charge them with a solar panel. Solar panels don't come with these unless you buy a bundle. Now, inside these solar generators, you'll see a lot of stuff. And these are made, this is the Jackery Explorer 1000. It's a teardown video of that. You can see the link to it. And you see a lot of the cylindrical cells in there. And you see a battery management system in there. You also see an AC inverter. And you see that this thing has 96 cells. So 6 series groups of 16 in parallel. And you can do the math and you see what you get there. So this thing will come out at about 83.5 amp hours, which is their 102 watt hours. So this has a lot more inside because you've got a lot more features. And there are many solar generators out there. And for example, you have a table here with some of these Amide, which uses NMC. Most of these use NMC. Go Labs down below is one of the few I've seen with lithium iron phosphate. The Goal Zero down below, many people know about the Goal Zero. What I don't like about the Goal Zero is compare the price to watt hours. It's way too overpriced. I don't see any reason for that. So, like I said, these all have the 10 amp output. The Go Labs is actually unregulated, so that's another thing to note about it. It's got a lower price there, but you got to do the price per watt hour and so forth. So most of these are made and sold through China on Amazon. I'm not sure if too many actually built in the US. Jackery and Goal Zero are probably the best well-known brands. I've been happy with both Jackeries that I had and tested, and they've worked quite well. And you could see from the teardown video, they're actually pretty well made. So let's compare the lithium iron phosphate battery to a solar generator. So let's look at a 100 amp hour battery and 102 watt hour solar generator. So 100 amp hour lithium iron phosphate battery is actually 1280 watt hours. So they're not exactly the same thing. It's 100 amp hours and 78 amp hours, but that's the way they build them. They both have 10-year life. I told you the discharge cycles are different. The depth of discharge is the same, 100% on both. Solar generator is a lot lighter, and that's lighter even with all those added features in there. It has the voltage regulation, at least most of the models that I've shown you there, whereas you don't get voltage regulation with the lithium iron phosphate battery. But we'll see in a minute, you don't really need that for lithium iron phosphate. They both have battery management system, and the solar generator has all these added features. But then when you look at the cost per watt hour, you're paying a lot more for those added features. So if you don't need those added features, then stick with the lithium iron phosphate standalone battery. And but if those features are convenient for you and you need to run your laptop, or you don't want to have a separate solar charge controller to charge your lithium battery and so on and so forth, the solar generator is quite convenient. So I got hold of these 3 different lithium iron phosphate batteries, Ampertime, Battleborn, and Bioino Power, and 3 different solar generators, 2 from Jackery, 1 from Max Oak. And I put them through pretty extensive testing over the last 2+ years. So my testing involves, I'll show you some of the bench testing results, but also running these things for a couple of months in my home observatory. And then each one was taken into the field for a real on-site test, at least once. And that would be typically 3 days or more out in the field. So I won't go through all the numbers here, but I show in this table the rated amp hours and the actual amp hours. So I measure these things by using a dummy load and running the battery down till the BMS shuts it off. So 100% depth of discharge. And I do that 3 times because I want to make sure that the results are consistent. And I will tell you, the results are always very consistent, a minor fluctuation from run to run. So you'll notice the ones in green, Ampertime and Battleborn, actually give you more than 100 amp hours, 103, 105. Battleborn actually designs their batteries to be 104 to 108 amp hours. And as I showed you before, when you add up the total amp hours in the individual cells, you're going to have to come out at least 102 amp hours anyway. So you won't hit exactly 100 amp hours because the capacity in the cells are quantized. And there's some variation to cell to cell. So you see the amp hours and the watt hours there. I like to work in watt hours because we measure the power in watts anyway. BioEno power, their 50 amp hour battery. I wanted to test the 50 amp hour battery, even though they make a range of batteries, including 100 amp hour, because not everybody needs 100 amp hour. And theirs came out to be about 45 amp hours, or 90% of its stated capacity. Now, that's not too unusual. There are plenty of other batteries and solars. You see two solar generators there, one from Jackery and Blue Eddy that only had 90% of their rated capacity. And whereas the Jackery 500 had 105%. So there are variations in the capacities from the build to build, but also some of this has to do with design to design. All right. Now, the second test is a voltage discharge versus depth of discharge. So I kept track of the voltage as I drained the batteries, and I have the curves here for a Battleborn battery in blue, BioEno in orange, Ampertime in gray, and Jackery in red. And the first thing you notice is the Jackery starts off at a lower voltage because it's regulated. And I'm putting a 60 watt load on here. So I picked 60 watts because that's probably a reasonable load for a astrophotography setup. It could be less, it could be more. Some are in the 30 watts. It depends on whether you're running a cooled camera or not, you're running a dew heater or not, you're running a Raspberry Pi, or you're using a laptop or whatever. So the Jackery starts at 12.75. It stays pretty flat because it's voltage regulated. And when it shuts off, it shuts off. It doesn't gradually decay, it shuts off. Whereas the lithium iron phosphate have a very slow roll off in their voltage. And then you see all the curves are basically the same. It doesn't matter which manufacturer, whether it was a cylindrical cell or a prismatic cell, they're all basically the same because it's just the chemistry in there. And I don't have on this one here, but the lead acid will drop below 12.06 volts, which is 50% depth of discharge at 50%, and it will drop below 12 volts period at about 48% depth of discharge. Whereas you see that the lithium iron phosphate batteries go from about 12.9 volts with a 60 watt load to 11.9 volts after 96% depth of discharge. So you're getting pretty close to 100% of what the battery is rated at with the lithium iron phosphate, and you're getting 100% with the solar generator. So you need to pay attention because this thing, you don't want to get down to the end and it shuts everything down. So you need to really know how long your battery will last, how many hours you can run with your load. And that means you really need to know what your load is. So the third thing I did were field tests with all of these. And this is a list of some of my equipment. Each test is a little different. Sometimes I needed the dew heater, other times I didn't. Sometimes I ran the my laptop with AC out of the, for instance, out of the solar generator, one of its AC ports, inverter ports, or I even put an inverter on one of the lithium iron phosphate batteries. So, I can't exactly run these identically each time, but you see some examples of the equipment I use. So I have a C11 on a mighty mount. I have an uncooled camera, and I have a guide camera. And I use a mini PC generally to run my equipment at the scope. And I use a wireless router. But I use my XPS laptop to manage what's going on the B-Link. Sometimes so that doesn't draw too much power. It draws about 30 watts that way. So what you need to do when you're going out in the field and you're not sure how much power you need to either measure or estimate your power needs. Now, I'm not going to go through how to measure it. There's a link at the end of this presentation. I've done a write-up on exactly how to do that, what equipment you need, how to set it up. I also have done a video on my YouTube channel, and I have linked to my YouTube channel at the end. So I can show you exactly how to measure the power used by your equipment. If you don't want to do that, you can take a look at this table, and things don't change that much from my equipment to your equipment. In fact, you can see here, I typically use this Dell laptop, and that thing runs about 36 watts when I'm running the SkyX and imaging. I also use the mini PC from B-Link when sometimes most of the time I use that to drive the SkyX, do the imaging and guiding. And you see that uses a lot less power. Now, Raspberry Pi, I don't have one, but it's pretty clear Raspberry Pis draw very low power, 4 to 6 watts. And the Sky Fusion is rated at about 4 to 8 watts. So you can see you're somewhere between 4 and 35, 36 watts, unless you have an older laptop that is pretty inefficient. So you can estimate what you're doing, how much power you're drawing from that table. I've also listed a whole bunch of mounts here. I have a MX mount. I have a, not MXT, MX mount. My Mighty mount is for in the field. I originally had a CGE. I have a CG5, Nexstar 6SE, ETX80. So, you know, it gives you an idea. And most people think mounts use a lot of power. Generally, they don't unless you have one of these high-end mounts. You can see the CGE, which is a pretty substantial mount, uses about 3.8 watts to do tracking. Now, when you do high-speed slews, it uses more. But if you're high-speed slewing all the time, I don't know what the heck you're doing. So don't assume much higher than that. So I don't own a cooled camera, but I did measurements on my friend's cooled camera. And you can see here at different settings, the set points, how much power that you use. It can be anywhere from a few watts at a mild cooling to as much as 20 or maybe even more, depending on the model that you have. The uncooled camera itself, these cameras don't use hardly anything. Guide cameras, don't even worry about them. Dew heaters, and that varies depending on what size of dew heater, so you can see things here. So the big power hogs are laptops, dew heaters, camera coolers. So if you were to buy a 100 amp hour lithium iron phosphate battery or a 50 amp hour battery, or use one of these solar generators, 1,000 watt hours or 500 watt hours, how long would it last for you out in the field? So I put this table together and to give you an estimate, and I came up with 3 ranges of equipment. So let's assume you use you don't use a laptop, which is power hungry. You use something like a Raspberry Pi, a Nuke, or a mini PC. You have a tracking mount, uncooled camera, a guider, focuser, filter wheel, and a powered USB hub. You're probably running 20 to 30 watts, not a lot. And you can see 100 amp hour battery, you can run for days without recharging that. So you maybe don't want a 100 amp hour battery, maybe only want a 50 amp hour battery or a 500 watt solar generator. Now, if you add to that dew heater and or camera cooling, that's going to put you in the 30 to 60 watt power draw range. And you see that your consumption, your time will come down accordingly. So now maybe you do want a 100 amp hour battery to run several days. And this would be running multiple days without having to recharge. And if you added a 15.4-inch laptop in place of a mini PC, you could be anywhere from 60 to 120 watts, depending on how you run that laptop, what software is on it, and whether you dim the screen or don't dim the screen. So you can see the amount of hours you can expect to run there. And in that case, I would suggest you want something with a lot of juice, a lot of energy in it. So again, the power supply size required will depend on the number, the runtime hours per night, how many nights in a row you want to go before recharging. And so any of the above power supplies that I mentioned here will take care of a 60 watt load for at least one full night without concern. Now, suppose you want to recharge. Well, it matters whether you have a solar generator or a standalone battery. So keep in mind, you can't charge these things below freezing, at least 25 degrees to 32 degrees. nor above 131 degrees. Hopefully nobody's near 131 degrees. So otherwise you will start to damage the cells in there. For AC charging, solar generators, as I said before, do come with an AC charger, and batteries will require a lithium capable charger. So that's because lithium requires a different charge profile from lead acid. If you use a lead acid charger, you're not going to fully charge the lithium battery, and you're ultimately going to damage it. If you're doing solar charging, the solar generators are convenient because they already have the charge controller inside. And you just need to make sure that the connector coming out of your solar panel is compatible with the connector on the input to the solar generator. So Jackery's panels are made for Jackery, and it'll work on some others as well. With a standalone battery, you see on the right, I have the Jackery solar panel there, and I have the battle-borne battery, but I need a solar charge controller, and it's not very difficult to set that up. So the power from the solar generator goes into the charge controller, and then it goes from the charge controller out. And that's because the charge controller is taking the current at something like 18.8 volts or maybe more and converting it into 14.6 volts, which is what anywhere between 14.2 and 14.6 volt to charge the lithium battery. Now, I did charge tests on all of these batteries and solar generators as well. Like I said, the solar generators come with their included AC charger, and you see those things charge pretty quickly, 6-7 hours. Now you might say, if you're paying attention, how come the Jackery 70 amp hour battery charges in the same time as the Jackery 43 amp hour battery? And the answer is simple. They give you a different AC charger. And so they're actually limiting the internal circuitry on that Jackery 500 is not taking as much juice as the larger model Jackery on purpose. And that will turn out to be the case when you put a solar panel on each of those. You see the Jackery 1000 charges on a 100-watt solar panel in about 11 hours. That's with good sun. And the Jackery 500, which is only, a little more than half the amp hours, is taking 9.5 hours. Again, that's because you're not getting all of the energy out of the solar panel into the Jackery 500 because it limits the current going in there. Now, with the lithium iron phosphate batteries, you have to have a standalone lithium charger. As I mentioned, I have a 10 amp lithium charger. You can use a 20 amp or 30 amp charger and charge much faster. But in that case, it's pretty simple. A 10 amp charger is going to charge a 100 amp hour battery in 10 hours. But since that battle-borne battery of mine rated out at 110 amp hours total, it took 11 hours to charge it, and that makes sense. And the ampere time came out at 103 amp hours, so it took 10.5 hours. Whereas the battle-borne was a little bit shy, and it took 4.7 hours. So the math works out. With the solar panels, it also makes sense because the two solar panels are probably putting out anywhere from 5 to 5.5 amps each at the 14.6 charging voltage. So you see the math works there as well. Okay. Okay, so let me wrap up. Lead acid batteries work. I'm not telling anyone to throw them away. If you like lead acid, have at it. But they're no longer the best choice. They are not the cheapest choice for certain. Lithium batteries have many advantages and they're gaining traction fast. You're seeing a lot more people moving to those. Solar generators are much more expensive than a simple lithium iron phosphate battery, but they do provide significantly more features, and I can see why people like those as well. So if you want more information, you can visit my website. I have a lot more detailed information on each of these batteries, solar generators. I have a full write-up and review of each one in the blog section of my website. I've done some YouTube videos on them as well. You can also find things in there that can help you with power in the field. So if you want to learn how to measure your own power with your own equipment, both DC and AC, I walk you through in one of the videos, and I also have a blog that written directions on how to do that. And if you're using something like a mini PC or an Intel Nuke, which actually operates at 19 volts, not 12 volts, it's very simple to use a DC to DC voltage converter. Convert your 12 volt output of the battery to 19 volts, and your computer will be quite happy. I do that with a 12 volt to 48 volt converter to run my software BISC mount, because software BISC mounts require 48 volts. And their solution for in the field power is the Ego battery, which is 56 volts and costs a fortune, not including the fortune for software BISC cable that you have to buy. This DC to DC voltage converter will cost you 25 bucks, and it's very simple to set up. So I show you how to do that. And my son used to use a DSLR camera, and those things run around 7.4 volts. So you can also take the 12 volts down to 7.4 volts and not worry about batteries and the camera battery going out while you're doing your exposures. And if you're trying to do any kind of wireless Wi-Fi setup connection, which is what I do, I have a step-by-step guide for that. And like I said, I started off in electronically assisted astronomy. So I've put together a whole series as a beginner's guide if you're interested in that. Any questions?
Thank you, Curtis. I was just observing the YouTube channel, and there are questions coming in there. So one question there is, what is your opinion on comet defense?
Comet defense?
Uh-huh.
Okay, that's outside the scope of this talk.
Yeah, I don't know if this was like, I wasn't sure if it was like a name of some equipment that you mentioned,
No.
and that's where it's coming up. Okay, all right.
I don't have anything to say about that.
Okay, all right, no worries. Anybody else have any questions? I have to say, I wish we had more folks from our astrophotography group, or we have inside SJAA, we have a separate subgroup. We call it SIG, or Special Imaging Group, who get together every month. They would have loved, like, I'm definitely going to talk.
Hopefully they'll watch the video.
Yeah, they should watch the YouTube video, or maybe they will have you come and give a talk in their meeting as well.
Well,
I don't know.
And on my website, there's a link. If someone wants to ask me questions, they can always send me questions. From there.
I mean, definitely it was more useful to anybody using electronically assisted viewing, as you mentioned. But I think I heard someone asking a question.
Yeah, I was just wondering, can we just talk up if we have a question?
Yeah, sure. Yeah, go ahead.
Okay. I just wanted to know, so I have a prismatic kind of battery. And I have two questions. One for that one, which is, you were saying, so in that LiFo prismatic cell, I don't need a power regulator or a voltage regulator. I built a little breakout box for it. So, it's each thing that I connect to it has a, has a like a fuse that doesn't allow it to draw too much
current. Yeah.
Current. But what about the voltage? Is that actually 12 volts coming out, or is that like 13 volts coming out of the?
All right. So let me try to answer your question. The regulation versus non-regulation has nothing to do with prismatic versus cylindrical cell. Okay. What I said is that the solar generators, let me go back here. Let's go back to, okay. So the,
guess what I'm saying is, you see that
The difference is in the chemistry, whether or not you need a regulation or you don't need a regulation.
but
Okay.
it's putting these type of batteries are putting out 12.8 volts, right? And my electronics are using 12 volts. Do I need to worry about that, or
Okay.
no?
All right. So let me answer. I'll give a full answer. So first of all, lithium iron phosphate cells come in at 3.2 volts nominally. Could be a little bit less or a little bit higher, but when I say a little bit, it's like 0.05 or something like that, 3.25 or something. So it'll come out at 4 of them in series, make 12.8 volts. It's very convenient. Nothing wrong with 12.8 volts for your electronics. If you had a lead acid battery and it was fully charged, it would be fully charged, would be anywhere from 12.6 to 12.9 volts. Okay. And all of our electronics is designed to work in that range anyway. It's designed to work at 13 volts, 13.2 volts. I'm not sure where the upper limit is on some of the equipment. There's no reason to worry about 12.8 volts or even 13 volts. You do not need to regulate that. Okay. So
Okay.
does that answer your question, first of all?
Yeah, that answers that question. So I don't need to worry about that. My second question is, I have a lithium-ion battery pack from Mead, and so I use that when I travel. Like if I'm taking my stuff on an airplane, I can't carry the big battery, right?
Right.
So
there's a capacity limit. Yep.
Right. Yeah. So I was just wondering on that one. Nowadays, when I charge it, it shows you levels like 1, 2, 3, 4, right on it. Like and it no matter how long I leave it on, it's still blinking at the 4. Is that just dropping in capacity? Is that what's going on there? Like it doesn't go solid to the at the last one. The last bar keeps flashing basically.
It does that when
I'm charging,
okay, so one interesting thing about lithium batteries, when you charge them, you'll see the capacity goes up pretty quickly, but when you get close to 100%, it slows down, and the last few percent of full charge takes very long compared to how fast it was charging from, say, 0% to, say, 96 or 97% state of charge. And I think that has to do with the battery management system kicking in and making sure that all the cells are being evenly charged, and it's being very cautious at the very end. So I noticed that whether I'm doing a solar panel charge or a AC charger, and it doesn't matter which battery or solar generator I'm using, it'll get like to 98%, and then it's like, man, it took a long time to go from 98 to 100. So maybe that's what's happening there, or maybe that's the design. I don't know whether they just flash that like that or
used to
not.
go solid. It used to go solid, and it doesn't anymore. That's why I was just curious if that's something I should be looking. I mean, is that like a drop in capacity, or
well, I mean,
never getting to 100?
You'd have to see whether you're able to last as long as you used to with the same. I haven't tested one of those Meads, so I can't answer that from specifics. Okay. And then you mentioned another thing. So I want to make sure everybody's clear. It doesn't matter whether you have cylindrical cells or prismatic cells. The cell voltage is dependent not on whether it's cylindrical or prismatic. It's dependent on whether it's lithium iron phosphate or lithium, nickel, manganese, cobalt oxide. And let me go back to that for a minute. The NMC, which is used in most solar generators, as I told you, it has a different cell voltage. And the cell voltage is typically 3.6, not 3.2. So 4 of those would give you 14.4 volts. So that's not what we want, right? So in fact, inside this Jackery 1000, and it varies by model of Jackery. The 500 is different than the 1000, and the 240 is different than that. So in the Jackery, they put 6 of those cells in series. 6 times 3.6 give you 21.6 volt. Hence the need for a voltage regulator, because you don't want 21.6 volts. That'll damage our equipment, and they know that. Most stuff that's designed to work at 12 volts works quite well at 13, a little over 13, whatever, but not going to work at 21.6. So that's why they have a regulator. And that's just due to the chemistry of nickel, manganese, cobalt technology. And it's perfectly good cell. It has lots of advantage. I told you it has a high energy density, so it makes these things lightweight. So anyway, and that's why this Ego battery, if you're familiar with Ego batteries, which you'll find at Lowe's and all these gardening tools, they're actually 56 volts. And if you do the math, you get 56 if you put a certain number of these cells in series. So they don't get the nice convenient 12.8 volts that you get out of lithium iron phosphate, but so what? It has a voltage regulator in there. And as I showed you on the voltage curve, it's flat. Okay, that's fine. It's flat at 100, all the way to 100%. Whereas I do lose the last 4%. If I don't want to go below 12 volts, say my equipment doesn't like the 11.9 volts, okay, I lose the last 4% on a lithium iron phosphate battery. So I only get 96%. But most things won't die at 11.9 volts. So
Thank you.
Hopefully that clarifies. And I don't know on that particular mead. Let's see. Is it this mead here, the 220?
Yeah, yeah, the 18. Yeah, that's it. That's it. Yep.
Yeah, I toyed with calling up Mead saying, hey, you want me to test yours too and publish it? But how many of these things I can test? I got to move on to some astronomy sometime.
And, they didn't have the best customer service when I called them either. So I don't know.
Well, if you look at the cost, they're like a little over $1 per watt hour. Some people like it because it has the convenient connectors, the 5.5 by 2.1 and all that other stuff.
That's exactly why I bought it, because it has 3 of those, and that was that instead of making a breakout out of one, that's the whole reason I bought that one over the Celestron.
Well, I would recommend the Jackery 500 instead, and it's you're also paying about $1 per watt hour for that.
I have traveled with that though.
Well, okay, on the airplane.
This is for travel. Yeah,
you're right.
This is for
you're
travel.
right.
Yep. Yeah.
The one thing about the Jackery 500 is they use this proprietary plug, and if you look on my website, I have links to the adapter, so that's a little bit of a pain. Whereas the Maxo uses 5.5 by 2.1. I try to tell Jackery, why are you using that plug? Well, nobody uses that. Who uses that? But I think CPAP machines or something use that, which is another market for them. Okay. Any other comments, questions?
I saw just now somebody else just joined. Thank you for joining. Hopefully you got some talk that you could see and listen to. And
is this talk also posted somewhere, the slides?
Yeah. So actually, we record all our talks and it's being live streamed right now. So the YouTube link is available in the meetup that you got the Zoom link from. And you can just go there and watch it later again. And the slides will be part of the presentation or the part of the talk, recorded talk.
Yeah, at some point here, maybe tomorrow or so, I'll post my slides on my website. And there's the website there. You can, California Skies, spelled with KYS because someone had the IES and I couldn't get the IES. So I misspelled, but that's the way it is. So I'll post it on there on my website tomorrow or the next day. And then you can pull the talk down from there, or you can watch the YouTube.
Yeah, thank you.
Anybody, I'm curious, anybody out there besides the one person, I guess, who was the one person? Was that Anil that?
Yeah.
Was that?
Yeah.
Okay. Anybody else use any sort of lithium power supply? Either nobody's talking or no one.
No, I mean, I was just thinking, I still use a manual telescope. So I keep thinking, I keep thinking that this would have been a very great talk for, or is SIG group, and I will definitely ping them to
Yeah, they
either
can watch the YouTube.
watch it.
Fine.
Yeah.
Okay.
Any other questions though? Comments, feedback for SJ? I'm here for that too.
I just want to say thank you so much. I got a lot out of this, and I appreciate this talk. And I will be checking out your website.
Okay, that's
Okay.
great.
Yeah,
All
that's
right,
good.
well,
I appreciate that. And you know, I went a little bit fast, but you can go, if you're really interested, you can go through this stuff. And my main messages are this: if you're gonna move to some kind of power supply in the field, don't go with lead acid. Don't go with AGM. Don't fool yourself that it's cheaper. It's not cheaper. Get some sort of lithium chemistry, whether it's a simple lead acid battery, a simple lithium iron phosphate standalone battery, or if you want all those bells and whistles and you can afford to pay more, you can get something like a solar generator. But lithium is really the way to go. You can easily recharge it in the field with, you can recharge lead acid in the field with a solar panel as well. But, trying to lug these 64-pound, 100-amp-hour lead acid batteries, it's just ridiculous. You're going to carry something that's 24 pounds and will last you twice as long. So lithium is really the way to go. Be careful what you buy. Investigate carefully, read the specs, read the reviews. And if you can find a teardown video, there's a guy named Will Prowse, Prowse. He does a lot of solar stuff. That guy makes a living out of it. And he deserves to make a living because he's pretty smart and he's enjoyable to watch. From time to time, you'll see him tear down these equipment. And that's the best thing to find. Well, what's inside? How are the wires that they put in there the proper gauge? If they're running 100 amps through there, they better be a significant gauge wire. How are they soldered together? How's everything spaced? Is stuff fused? You can see all that kind of stuff. And I put some of those teardown video pictures in this presentation. So don't just go buy something that's the cheapest. And Goal Zero, everybody, Goal Zero. Look at the price. There's nothing they're offering there, as far as I'm concerned, that justifies that price. So anyway, do your homework. All right. Thank you for your attention and the opportunity to present to you.
Definitely. Thanks for coming, Curtis. This was great. Thank you so much. And
Okay,
good night,
thanks.
everyone.